things for the second time. When I decided to speak about these things, I was confident to make some progress, which didn't come, but then I didn't change the subject. So the starting point is the Brunn-Minkowski inequality. And it says that if you take two convex and compact sets, K1 and K0, in Kn, which is the family of convex bodies, E over n, and you take T between 0 and 1, then the volume of the convex linear combination of K0 and K1, so 1 minus T K0 plus T K1 to the power 1 over n. This is bigger than the convex linear combination of the volume, with the same power. So this is Brunn-Minkowski, and Brunn-Minkowski is a model for other inequalities of the same form. So in general, you may have a functional f from Kn to the positive reals, and this functional should be homogeneous. Of some order which, for simplicity, I will take different from 0. And then you say that f verifies an inequality of Brunn-Minkowski type if exactly the same holds with the, so I'm sorry, Vn is the volume, which means the Lebesgue measure. So if everything holds in this form, so f of 1 minus t k0 plus t k1 to the power 1 over alpha is bigger than 1 minus t f of k0 to the power 1 over alpha plus t f of k1 to the power 1 over alpha. For every k0, k1, and t in the same form. So if you have a behavior like this, then you say that f verifies a Brunn-Minkowski type inequality. I didn't say it, but I hope it's clear. From the context, here I'm using the Minkowski addition. I will not recall the definition, but in case of any single question, just interrupt me. I will be very happy to answer. There are examples. Of course, I mean, this definition makes sense because there are examples. Beyond the volume. And maybe the first example is given by intrinsic volume. Every intrinsic volume verifies the Brunn-Minkowski inequality with a different order of homogeneity, and this comes basically from the Alexandrov-Frenkel inequality. But the type of example I want to speak about today is of a completely different nature. And these are examples coming from mathematical physics. I will refer to them as to variational functionals. This subject is not new, but maybe is less known to this audience. Anyway, there are three main functionals. One is the principal frequency of a convex body. And the Brunn-Minkowski inequality for the principal frequency was proved by Braskamp and Lieb. In 1976. And then there is the capacity of a convex body, the electrostatic capacity in a physical sense. And this was proved by Borel in 81, that the capacity verifies a Brunn-Minkowski type inequality. And then there is the third example, which is the torsion. Or torsional rigidity is a variational functional I will not have time to speak about, but roughly speaking is the resistance of a column with a certain section to torsion. Is a set functional with some order of homogeneity, and it verifies Brunn-Minkowski type inequality exactly in this sense. And this was again proved by Borel, Christopher Borel in 1985. The aim of this talk is to present an extension of the Brunn-Minkowski inequality for the principal frequency to the Gauss space, from the standard case to the Gauss space. So what I will do is to speak about the principal frequency in the standard situation, including the definition, and then I will pass to the Gauss space and present our result. So this is what I want to speak about. So what is the principal frequency of a convex body? So you take your convex body K, and you take a function which is continuous on your set, and which is also C1 in the interior of your set. So you need the gradient to define this object, and then you consider this ratio, the integral of the gradient of V norm squared over K divided by the integral over K of V squared. So the L2 norm square of the gradient over the L2 norm of the function. This ratio I will denote it by R of V, and R is because of Rayleigh. This is the Rayleigh quotient. And then you minimize, of course, sorry. V has to be not identically equal to 0, otherwise you divide by 0. And then you minimize. You take the infimum over all possible choices of V, of the Rayleigh quotient. And by definition, this is lambda of K, is the principal frequency of your domain. Yes?
Are you specifying boundary conditions? Or?
Thank you very much. Thank you very much. With zero boundary condition.
Why principal frequency?
Because if you have a drum, assume you have a drum with the shape of K, then you beat the drum and you hear a sound, and the sound can be decomposed in frequencies. Okay? The lowest frequency is this number. So is the lowest sound, the lowest tune that you hear.
One more question.
Yes.
Do you have something like continuity here?
Of the functional, or
Yeah, of lambda.
yes. I will list some. Wow.
Not so good.
Not so good.
There is here.
I am not able to use it.
I know. Me neither. But this doesn't work. Come on.
No.
Please.
Should I try? But then I have to wait.
Try. No. You use me on the other side.
I'm sorry. I mean, I didn't want to.
No, don't worry. I'm not able either.
Participants should be warned.
But then, after this operation, I can use it immediately?
Yes.
Are you sure?
If you do it properly.
How do you do your undergrad?
Yes, also in Austria. I was surprised.
How much time do I have for this talk?
You'll see.
This was not computed in. Okay, so this infimum, in fact, is there exists a minimizer U, and the fact that it is a minimizer implies that U is the solution of some differential equation. In fact, the U is the solution of this equation here. With zero boundary condition. So in fact, lambda is the first eigenvalue of the Laplace operator in the domain with Dirichlet boundary condition. Now, this symbol here is the Laplace operator. And it's just the trace of the Hessian matrix. So lambda has many names. It's the principal frequency, but it's also the first eigenvalue of the Laplace operator with zero boundary condition. And of course, lambda is also the best constant in the Poincare inequality, just by the definition, because now you know that lambda k times the integral over k of v squared is smaller than the integral over k of grad v squared for every v such that they are zero on the boundary of k. So it's the optimal constant in the Poincare inequality with zero boundary condition. Now, properties. So lambda is a rigid motion invariant. It doesn't depend on the position of the set. It's continuous. Just to reply to the question by Carsten, is -2 homogeneous, which means that lambda of sk is s to the power -2 lambda of k for every positive s, which means that if you shrink your drum, you hear a very high frequency sound. It's also monotone decreasing with respect to set inclusion. Now, these are basic properties, but there is one more property which is very interesting. It's called the Faber-Krahn inequality, but in fact it's an isoperimetric principle. And it says that lambda of k is bigger than lambda of b, where b is a ball with the same volume as k. So among all convex bodies with the same volume, the ball has the minimal principal frequency. This is just the isoperimetric inequality for lambda. And behind this result, which is very well known in the realm of PDEs, behind this result there is the Polia-Zigo principle, which says that the Rayleigh quotient, which is still written there, is decreasing under Steiner symmetrization, which explains everything, because you symmetrize and you go down, you symmetrize many times, you go to the ball and the lambda is going down. So it's basically it's the proof of this one. Now, the theorem I was referring about the Brunn-Minkowski inequality for lambda says that for every k0 and k1, and for every t between 0 and 1, lambda of 1 minus t k0 plus t k1 to the power minus 2, minus 1/2, is bigger than 1 minus t lambda of k0 to the power minus 1/2 plus t lambda of k1 to the power 1 minus 1/2. So this is just the Brunn-Minkowski inequality for lambda. You see that the exponent is the reciprocal of the homogeneity exponent. This theorem, as I said, was proved by Blaskamp and Lieb in a very rich paper. In fact, they proved a weaker inequality. I want to mention this weaker form because it's important for the sample. So they proved that lambda is convex. Here it says that lambda is minus 1/2 concave, but they proved this. This second inequality is weaker than the first, but by homogeneity, from the second you get the first. But to pass from here to here, you need the fact that the functional is homogeneous. Otherwise, you don't get the optimal one. This is optimal. I mean, this is the sharp exponent. You cannot do anything better. This is not optimal, but it's equivalent to this. In the Gauss setting, this equivalence is not true anymore. So, and this will come out at some point. Let me tell you that in the same paper, basically on the same page, they also proved another interesting fact. They proved that the solution to this problem has a geometric property is log concave. So if I go back here, you have your domain K, and you have the first eigenfunction of the Laplace operator, which looks more or less like this. And this function is log concave, which was an open problem in PDEs for a while, and then it was solved by Blaskamp and Lieb. And the proof of the two facts are really connected. It's the same proof in some sense. And this happens frequently, that the Brunn-Minkowski inequality for some functionals in the calculus of variation is connected to some geometric property of the solution to the corresponding Euler-Lagrange equation. I don't know whether there is a reason for that, but it's a fact.
To what extent is it important that K0 and K1 are convex?
This is a very good question. It's not important at all. The result by Blaskamp and Lieb is true for general domains, but for simplicity, I wanted to state this result for convex domain. But the proof is very general. Equality conditions require convexity, like in many other situations. I'm doing a mess. I'm sorry. So we now go to the Gauss setting. So from now on, I will be considering Rn with a Gaussian measure. Let me see whether I'm not forgetting anything. So d gamma n of x is just 1 over 2 pi to the n over 2 times e to the minus norm of x squared divided by 2. This is the standard Gaussian measure. So first question, what happens to a Brunn-Minkowski? There are many answers. The first is the multiplicatory form. Which says that gamma n of 1 minus t k0 plus t k1 is now bigger than the geometric mean, gamma n of k0 to the power 1 minus t times gamma n of k1 to the power t. This basically is Kirchhoff-Riemann. Okay? Then we have another inequality, which I will just write by the name, because I want to mention it, but I will not just use it. Erhard inequality. This is stronger than the multiplicative BM, and it's strictly connected to the isoperimetric theorem in Gauss space. I will come to this later on. And then there is also the dimensional Brunn-Minkowski in Gauss space. So there is exactly the Brunn-Minkowski inequality with the Lebesgue measure replaced by the Gauss measure. So gamma n of 1 minus t k0 plus t k1 to the power 1 over n. And here you have gamma n of k1 to the power 1 over n plus t gamma n of k0 and k1 to the power 1 over n. But here you need that k0 and k1 are origin symmetric. So of course this is stronger than BM. Apparently it's independent of Erhard. And let me tell you a little bit about the story, the history of this inequality. The question was posed by Gardner and Spavich in 2010. And then there was a counterexample showing that origin symmetric, it's a necessary condition. And this was proved by Nayar and Koch in 2013. And then there was a contribution, an important contribution with exponents 1 over 2n instead of 1 over n by Kolesnikov and Livshyts. And this was important because it's close to the result, and it was also an important step for the final solution of the result, which was given by Eskenazis and Moskidis. And they give the solution. So, I mean, they prove this inequality. Now I will introduce our functional after this preamble. So the Gaussian principal frequency, and the definition is really natural because you will see more or less the same definition as in the Lebesgue case. So you have your convex body. Again, you take a function which is continuous and C1 in the interior, and which is 0 on the boundary of K. And you just define the Gaussian Rayleigh quotient of V, which is what you imagine. So the L2 norm square of the gradient in V gamma n over the L2 norm of the function again avoiding the function which is identical equal to 0, and then you minimize. You define lambda gamma of K as the infimum of the Rayleigh quotient R gamma of V over all possible V. Again, there is a minimizer, but now the minimizer verifies a different differential equation because the measure is different. So there exists a minimizer. I hope you will be able to see here. I will write the problem here. So now the operator is not just the Laplacian, but is the Laplacian minus this first order term. So Laplacian of u minus grad u scalar x equal to minus lambda gamma k times u. So now the minimizer is the eigenfunction of a different operator. This operator is called the Ornstein-Uhlenbeck operator, or the generator of the Ornstein-Uhlenbeck semigroup. And the boundary condition are the same. So this definition is not new. It appears in a paper by Herald, which he published shortly after the famous paper on Herald inequality. And I will now tell you about some basic properties of this function. So we have lambda gamma of k. Now this is just rotation invariant. There is no homogeneity, like the volume, and there is no translation invariant, because the measure is not translation invariant and the measure is not homogeneous. It's continuous. And there is an isoperimetric inequality. This is very interesting. In 1984, in this paper, Herald proved that for every k, the principal frequency of k, the Gaussian principal frequency, is bigger than the Gaussian principal frequency of a half space, not a ball, but a half space, with the same Gaussian measure. So where H is a half space such that gamma n of H is equal to gamma n of K. So the situation is completely different with respect to the Lebesgue setting. Here you have your convex body. You find a half space, which I mean in any direction because you have rotation invariance, with the same Gaussian measure as K, and then you have this inequality. So this is Faber-Cran in Gaussian setting. And this is not surprising because, of course, this is very similar to the fact that for every k in Kn, and more generally for every Borel set with a good perimeter in the Gaussian sense, the Gaussian perimeter of K is bigger than the Gaussian perimeter of H, where H is a half space with the same Gaussian volume as K. This few lines are the Gaussian isoperimetric inequality, very famous. This was proved by Borel and then Sudakov and Cyrelson in 75. And then there was another proof by Gerard in 1983. And the idea of Gerard is to use a symmetrization procedure to prove the isoperimetric inequality. But in fact, Gerard is not symmetrizing, is desymmetrizing. So instead of taking the Steiner symmetrization, which doesn't work in this context, he was taking a symmetrization leading to half spaces instead of leading to the ball. So a completely different geometric procedure. And in this second paper of 1984, 1 year later, he was applying the same procedure to this functional with the same outcome, exactly the same. And here I want to notice that in the same paper, he considers also the Gaussian capacity and torsion, which are the two other functional that I mentioned at the beginning, and he's able to prove the same isoperimetric principle for the capacity and for the torsion.
Is convexity necessary?
So convexity is not needed here, and is not even needed. I'm eluding your question because I don't know the answer.
It's not needed here.
Sorry?
No convexity.
Here as well.
The co-area formula after that.
Thank you. So, in fact, in the first version, the result by Erhard was for convex sets. Erhard inequality initially was proved for convex sets. There was another paper by Christer Borel later on, which was extending Erhard inequality to non-convex sets. But this is for the perimeter. For this, I didn't remember this fact. So, our theorem so it's with Elisa Francini, Galina Livshyts, and Paolo Salani. Elisa and Paolo are from my department. Says that for every K0 and K1, and for every T in 0, 1, you have that lambda gamma of 1 minus T K0 plus T K1 is smaller than lambda gamma 1 minus T lambda gamma of K0 plus T lambda gamma of K1. So it's a concavity, sorry, a convexity inequality. Exactly similar to Braskamp and Lieb inequality in a weaker form, and we cannot pass from this weaker form to the stronger form because we don't have homogeneity, not directly. So we just have this for the Gaussian principal frequency. And moreover, if K0 and K1 are regular enough, meaning C2 alpha plus for some alpha between 0 and 1, this means that it's not enough to be C2 plus, C2 and positive Gaussian curvature. You also need some older continuity of the second derivative, and equality holds. Then, and this is very rigid, K0 has to be equal to K1, no dilation admitted in this case. So they really have to be the same. Of course, we don't know whether this inequality is optimal. We don't have conjectures for the optimal inequality maybe with the exponents for centrally symmetric, but this is not clear. And we also proved that, and this is related to the proof of this theorem, we also proved that the minimizer U is log concave. So we have the same behavior. So you see in the definition of gamma, attached to gamma there is a function, always. And the function is the solution to this problem. And just like in the back case, we proved that this has to be. Do I have some more minutes? So I want to show, as it was mentioned in the previous talk, that this is the only connection to the previous talk. It's important also to show the argument of a result. And so, so the proof. Here you have K0, here you have K1, here you have KT, which is 1 minus T K0 plus T K1. Here you have your solution U0, and here you have your solution U1. There will be a solution here, but I don't care. I will build a test function rather than the real solution. And we do the following. So we define U tilde T of Z as the supremum of U0 at x to the power 1 minus t times U1 at y to the power of t, where 1 minus tx plus ty is equal to z. Which means that we take a point z here, we write it as a linear convex combination of a point x and y, we form the geometric mean of the values, and we take this geometric mean, and then we maximize. This is a well-known operation. This is the operation which is behind the Hopper-Lindler inequality, more or less. And if you go to the exponents, so if you write U0 as e to the minus W0, U1 as e to the minus W1, and U tilde t as e to the minus W tilde t, then you are doing the following. W tilde t is just 1 minus t W tilde 0 star plus t W tilde 1 star star. So this is the infimal convolution, which is a well-known operation in convex analysis. This is defined by Rockefeller in his book. And many things are known about this function. This will not be the solution here. It will be a positive function here. It will be 0 on the boundary, because they are 0 on the boundary, and boundary points come only from boundary points. And it will not be a solution, but if you play with all the information that you have, and it's really simple, I mean, there is nothing mysterious behind, you get that the Laplacian of U tilde t minus the gradient of U tilde t scalar z is bigger than minus lambda t times U tilde t, where lambda t is 1 minus t lambda of k0 plus t lambda of k1. So you get a differential inequality, not a differential equality. Okay? And what do you do with that? You multiply by u tilde t, both sides, and then you integrate. And now here, everything looks very complicated, but then here you integrate by parts. And you use that this is the right operator to integrate by parts against the Gaussian measure. And this will give you exactly the L2 norm of the gradient.
Which K?
Sorry?
Which K?
KT. Thank you very much. With a minus sign. So, if you join this and this, you get that the Rayleigh quotient of W tilde T is smaller than lambda T. You change the sign, you divide by this, and you write what you get. But this is bigger than lambda of KT, by definition. So lambda of KT is smaller than lambda T. And this is the end of the proof. I have to say that the same proof works in the Lebesgue case. So this is not a new argument. The only fact is that it works also in the Gaussian setting. In the same, yes.
So what makes the Gaussian special in the sense that you do it for any local coordination, it works?
This is a very good question. If I can take a few more minutes, I will conclude with the open question. This is the end of the proof. So let me just exchange the blackboard. Maybe I will only need this part. So open question, open problems. Which in fact for me are closed problem because we tried a lot and I don't want to try any longer. but anyway, in general, I don't know the solution. So the first is extension to more general log concave measures. It's strange because we tried, but the technique does not extend. So for the moment, the technique fits perfectly the Gaussian measure, but at least as far as we tried, no other.
Neither of the 5 techniques.
Sorry?
Neither of the 5 techniques that we tried.
Yes, we have several ways to prove our results, but none of them applies to more general log concave measures. Oh, let me tell you one thing. This is very important. For this theorem, we received a very nice suggestion by Emanuel Millman, and one of the proofs presented in the paper is due basically to him. So this is one of the ways that we have to approach this theorem. It's not the only one, but it's one of them. And but they don't work in general. And so is there a dimensional Brunn-Minkowski inequality for lambda gamma? So can we write this inequality with exponents, with some exponent? This we also don't know. And the third is what about the torsion, and the capacity. So the other two examples, which are very well known in the Lebesgue setting, for which there is an isoperimetric inequality also in the Gaussian setting, but for which we are not able to establish exactly the same result as here. Thank you very much.